This example, it's kind of a long one, but it's a nice one and it incorporates a lot of the things we've been doing so far from this chapter and from the previous one. So this one's going to take us a little bit of time to go through, but I think it is going to be worth our while as we go. A long straight wire carries a current of 1 amp. We've called that I1 for 1 amp, and we see that that current flows down. A nearby conducting loop carries current of 2 amps, and it shows that the current comes around counterclockwise. First question, find the magnetic field at the left and right edges of the loop due to the wire. So we want the magnetic field at the left and right edges, so let's start with the left edge. The magnetic field is due to a long straight wire. So B at the left edge, BL for left, is mu naught times the current in the long straight wire, that was I1, divided by 2 pi times R1. R1 is the distance from the long straight wire to the left edge of the loop. There's our R1. Mu naught is our constant permeability of free space, 4 pi times 10 to the minus 7 Teslas meters over amps. R1 is 1 centimeter, so we'll put our numbers in. I'm not going to write out mu naught every time. You can just put that in your calculator. Current is 1 amp divided by R1, which is 1 centimeter from here to here, is 0.01 meters. And that gives a magnetic field of 2 times 10 to the minus 5 Teslas. Magnetic field, of course, is a vector. It has a direction. The current points down this way. The magnetic field makes big circles around the wire. What's the orientation of those circles? You get that through the right-hand rule. So you put your thumb with your current. Oh, I got to turn the page around. There we go. So your thumb goes with your current. Over here where the loop is, we ask, what are these circles doing? Well, they're coming up out of the page. So my thumb is with my current. On this side, it's coming out of the page. This side would be into the page. So over here on the side where the loop is, the magnetic field comes out of the page. If we put in a coordinate system, positive x to the right, positive y up, positive z out of the page, then our magnetic field vector is 2 times 10 to the minus 5 Teslas out of the page, or k hat. And we can draw that if we wish. So there's the direction of the magnetic field. Over here on the right-hand side of the loop, B on the right-hand side is mu naught I over 2 pi times R2. R2 is the distance from the wire to the loop. So there's R2. That distance is 1 centimeter plus 1 centimeter, 2 centimeters. So we can put in our numbers. And we get a magnetic field of 1.00 times 10 to the minus 5 Teslas, also out of the page, or k hat. Okay, part B, and we can draw that as well. There's our magnetic field, which also points out of the page. Part B, find the average magnetic force on each edge of the loop. So here's where we know that the force on a current-carrying wire, because this is a current-carrying wire, is equal to IL cross B. So we've got 4 sections. We've got the left, the bottom, the right, and the top. So let's start with the left-hand side. The force on the left-hand side of the loop is I2, the current in this part, times the length of that side, crossed with the magnetic field that it's sitting in, B of the left-hand side. Okay, the magnitude of this vector is going to be I2 times L times B of the left-hand side. Let's get the direction. So the current I2 comes down this way. There's our current I2 all the way around the loop. And we'll just draw it everywhere because we'll want it on each part of the loop there. So there's I2. So to find the direction of the force, we use our right-hand rule, or you can just do the math, it doesn't matter. L and I are in the same direction. I'll use the right-hand rule. Point your thumb in the direction of L, your index finger in the direction of B, and then your middle finger shows your direction of force that's pointing to the left. So I, L, cross B gives force. So there's the force on the left-hand side of the loop. Force on the left. So that direction is to the left. That would be the negative x direction, or minus I hat. Now we can put our numbers in. I2 is 2 amps. The length means the length of this section of the wire, which is 4 centimeters, times the size of the magnetic field on the left part of the loop, 2 times 10 to the minus 5 teslas. Put that through the calculator and we get a force of minus 1.6 times 10 to the minus 6 newtons in the x direction. Next, let's do the force on the right. Before we get started, ask yourself, do you think those forces will cancel or no? Okay, so you think if they'll cancel or not. Let's find that force on this part of the wire. Let's do the direction for it first. So the current is up. Magnetic field is out of the page. We see that the force points towards the right. So the force on the right-hand side of the loop is I2L cross the magnetic field on the right side of the loop. The direction is to the right, or plus I hat. Our current is still 2 amps. Length still 4 centimeters. Magnetic field on the right is 1 times 10 to the minus 5 teslas. So the magnetic field is 0, or the magnetic force is 0.8 times 10 to the minus 6 newtons I hat. Those forces don't cancel. That's because the magnetic field out here is weaker. The further you are away from a wire, the weaker the field is. And if the field is different, the force is different. Okay, so our force on the right points this way. Let's do the top and the bottom next. Let's get the direction of the force on the bottom. The first part, find the average magnetic force on each edge of the loop. So let's find the force at the middle of the loop. So we could find it if we wanted to find it properly. If you wanted to find the net force, it would work out to be the same as the average force. But if you wanted to find it for real, the force on the bottom of the loop, you'd have to do I2 dl cross B, because the magnetic field changes as you go across. We're going to do the force on the bottom, average, which means we'll do I2 L cross B, and we'll take the B at the middle. So that B is going to be mu naught times current I1 over 2 pi times the distance to the middle. So mu naught over 2 pi times 1 amp. Distance to the middle from here to here would be 1.5 centimeters. So that magnetic field would be 1.33 times 10 to the minus 5 teslas, and the direction would be out of the page. Okay, so the direction of the magnetic force on the bottom part of the loop, current goes this way, field goes up, force comes down. So we've got minus I2 L B on the bottom, J hat. So minus 2 amps times the length of the bottom part, that was 1 centimeter, times the magnetic field that we just found, so the magnetic field strength at the middle of that wire, J hat, gives us a net force on the bottom part of the loop of minus 2.67 times 10 to the minus 7 newtons J hat. And the direction on the bottom was down. And next we want to know the net force on the top of the loop, F on the top. So the direction is I cross B, gives us our force, points in the positive y direction. Something to recognize here is that the two magnetic fields will be the same, I2 is the same, and the length is the same. So IL cross B will give you equal and opposite. So your force on your top average equals minus force bottom average equals plus 2.67 times 10 to the minus 7 newtons J hat. Okay, so the force on the top is equal and opposite the force on the bottom. That's due to the symmetry of the situation. Part C, find the net force on the loop. So the net force is going to be the sum of all the forces we've found so far. So part C, F net is going to be the force of the left plus the force of the right plus the force on the bottom plus the force on the top. We know right off the bat that those guys give you 0. They're equal and opposite, so I'm not even going to write those down. Force on the left was minus 1.6 times 10 to the minus 5 teslas. Force on the right was 0.8 times 10 to the minus 5 teslas. Gives us a net force of minus 0.8 times 10 to the minus 5 teslas I hat. So the net force is to the left. Next question, part D. Find the magnetic moment of the loop. So this is dealing with the loop by itself. We'll have to remember, how do we find magnetic moment? So magnetic moment has a symbol of mu. We know that mu is current times area. The current is the current of the loop, and A is the area of the loop. The area is going to be length times width. And to get our direction, we have to use our right-hand rule. So the current in the loop goes around this way. To use the right-hand rule, you put your fingers, you make a circle with your fingers that represent the direction of the current. So my fingers are coming around counterclockwise. Your stuck-out thumb is your area vector, so that's k hat out of the page. So your area vector is length times width times k. So length times width in the k direction. So our magnetic moment there is 2 amps. The length is 1 centimeter. The width is 4 centimeters. Direction is k hat. So the magnetic moment then is 8 times 10 to the minus 4 amps times meters squared k. And there's the magnetic moment. The next part, part E, find the net torque on the loop. So let's see if we can figure out what the torque is going to be. We can do torque in a couple of ways. We can do torque is equal to R cross F. That's perfectly legitimate. Or maybe a faster way is to remember that the magnetic torque is equal to mu cross B. So the magnetic moment of the loop crossed with the magnetic field that it's sitting in. The magnetic field that this loop is sitting in is due to this wire, and the direction of that magnetic field is out of the page. So this B is from the wire, and the direction of this guy is k hat. This mu is of the loop. The direction of this guy is k hat. So our torque is something k hat cross something k hat equals 0. So when you take the cross product of two parallel vectors, you get 0. So what that tells us is that if we pull this one to the left and this one to the right, it won't rotate, and that makes sense. Okay, so no rotation there. That leads us into question F. If the loop is free to move, what would its motion be? So that's the next part. If we let the loop move, what happens? So let's think about what do we know about the forces. So for part F, we know that the net torque is equal to 0. That tells us that there's no rotation. And we know that our net force is in the negative I direction. So this tells us that if the loop were free to move, it would accelerate towards the left. And then if you wanted to think about it even further, it's enough to stop there, but if you wanted to think about it more, you would recognize that as it gets closer to the left, the magnetic field gets stronger. If the magnetic field gets stronger, then the force gets stronger and the acceleration would increase. So the acceleration would increase as it moved towards the left until it smacked right into that wire. Okay, last part, G. If current I1 is switched off, what happens? So that's an interesting question. That brings in our chapter 30 ideas. So let's ask what happens if we turn off current I1. So if we switch off I1, G, switch off I1. So if we turn off I1, the first thing that's going to happen is the magnetic field will go to 0. So B1 goes to 0. What does that mean is going to happen? So we'll just redraw the loop here. The magnetic field was out of the page. We had figured that out with our right-hand rule. So B1 was out of page. Lenz's law says if we change a magnetic field, so we go from out of page to 0, if we change a magnetic field, nature will create or induce a new field that will oppose that change. So if we apply the idea of Lenz's law, a new field, the induced field, will be out of page. So the induced field out of page. And the induced field is out of the page because this field went to 0. So our induced field will be out of the page to try and maintain that out of field page. If the induced field is out of the page, then it means that the induced current is going to be counterclockwise. So I imagine I'm grabbing this part of the loop. My fingers are coming out of the page here, shows my thumb is going up. So my induced current will be counterclockwise. Well, we already have I2 is counterclockwise. So what happens is that the net current in that loop will increase. Okay, so by changing the magnetic field of the wire, we get a new induced field, which induces the current, which is in the same direction of the existing current, which means that we get the net current increased.